Hello, everyone. So this is lecture 4 of our Möbius Inversion mini-series lectures. In the last two lectures, we focused on the function mu and its properties. Today, we're going to switch perspective. Instead of looking at single functions, we define a way to multiply two arithmetic functions together. The operation is called Dirichlet Convolution. It mixes the value of two functions along the divisors of n, and it turns out to be natural algebra behind divisor sums. Möbius inversion and many identity in number theory are going to be based on this. So in particular, we're going to see the definition and the special function of identity and epsilon, and work through the classic example of convolution of 1 by itself, which is tau n, is kind of the number of divisors of n. How do we watch this lecture for? You need to treat Dirichlet convolution like a new kind of product. Instead of multiplying the value at the same n, we combine the value of all divisor pair, kind of a d versus n over d. That's really important here. And we're gonna watch how 1 and epsilon, a special function, how they would act on a function under the operation of convolution operation, right? This lecture is actually very, very important. Make sure you understand it before you move on, because it is fundamental in the further lectures. All right, let's get right into the lecture.
Last time we met multiplicative arithmetic functions, like the constant 1 function or the totient. These assign a value to each positive integer, and when two numbers are coprime, the value at their product is the product of the individual values. Today, we ask a new question. Is there a natural way to multiply entire functions together, not just their values as single numbers, in a way that respects this multiplicative structure?
So we are not just plugging in numbers anymore. We want an operation that takes two functions, f and g, and makes a new function that still plays nicely with primes and divisors?
Here is the definition of Dirichlet convolution at the top. To get the convolution of f and g at a number n, we list all divisors d of n. For each divisor, we look at the pair d and n over d, evaluate f at the first and g at the second, and add all those products. So the new function mixes f and g along the divisor pairs of n.
It feels like we are scanning through all the ways to factor n as d times n over d, asking what f and g think about those two pieces, then combining them into one blended value at n.
Now we introduce two especially important functions. The first, called 1, just outputs the number 1 for every input n. That is what the first line on the slide says. The second, epsilon, is an indicator for the number 1. The bracket notation means epsilon of n is 1 only when n equals 1, and 0 for every other integer. You can picture epsilon as a single spike at 1 and 0 everywhere else.
So in convolution, 1 is like a uniform background, while epsilon is like a sharp unit at the starting point that we might hope will act like an identity element.
Let us use these special functions in the convolution formula. If we convolve 1 with itself, then for a fixed integer n, every divisor d contributes the value 1 times 1, which is just 1. So the convolution at n is simply the number of divisors of n. That function is usually called tau. For example, the computation on the slide shows that 12 has 6 divisors, so the convolution at 12 is 6.
So Dirichlet convolution with constant functions is already encoding basic number theoretic data like divisor counts. That makes the operation feel very natural, not artificial.
Dirichlet convolution behaves much like ordinary multiplication. The identities here say that it is commutative, so f convolved with g is the same as g convolved with f, and associative, so you can group three functions in any order. The third identity says epsilon acts as a multiplicative identity for convolution. To make this concrete, the example at the bottom checks associativity when all three functions are equal to 1 at the number 6. Both groupings give the same total, 9.
So once we know these laws, we can think of arithmetic functions as forming a kind of ring under pointwise addition, and this convolution product, with epsilon playing the role of the number 1?
Let us step back. Dirichlet convolution takes two arithmetic functions and blends them using all divisor pairs of each integer. Constant 1 and epsilon are special. Their convolutions give simple objects like the divisor, count, and leave other functions unchanged. These properties mirror the behavior of usual multiplication, which is why convolution is so powerful.
And the teaser equation with mu and 1 says there are functions that act like multiplicative inverses under convolution, right? Next time we will see how mu undoes the effect of summing over divisors.
Before we finish, try the exit ticket. First, use the definition of convolution to write the convolution of f with epsilon at n as an explicit sum. Remember that epsilon is 0 except at 1, so almost all the terms vanish. Second, express the convolution of 1 with f at n in terms of the values of f at the divisors of n.
So for f convolved with epsilon, I expect the only surviving term is the one where the divisor is exactly n, which should give back f of n. And for 1 convolved with f, we should get a sum of f over all divisors of n, since 1 does not change the values.
Exactly. Reflect on what these answers say. Epsilon picks out a single divisor contribution, while 1 does not filter anything and instead accumulates all divisor information. That contrast captures two extreme ways convolution can blend data across the divisor structure of an integer.
Thank you for your time in watching this. Please like, share, and subscribe to the channel. Of course, we always would like to hear from you. Please make your comments below.